Using a GDC to define functions and find derivatives is really quite straightforward. There's more to it than what I'm going to show in this video, but here are the basics. First of all, the common notation for the graphics display calculator is use F1, F2, F3, F4 to define a whole bunch of different functions. So I've created a brand new document, which is a calculator. And I'm typing in F1 bracket X bracket, and then I'm going to use Control and then this button here. You can see it's a colon equals there in blue there. And this is the way we define a function. So I'm going to define a really simple function. I'm going to define Control ln of x squared plus 1. So when I define it like so, it'll just say done, and it means that under the variable button here, I've got f1 defined. So what? The useful thing about that is that let's just say I wanted to work out what the value of f1 of 2 is. I just type in f1 of 2, and it gives me the exact value, ln 5. 2 squared is 4 plus 1 is 5. That's not that exciting, but control equals gives me the approximation of 1.609. So that's nice. But let's go one step further. I'm now going to define a second function, f2 of x, same way, control colon equals. And I'm going to go up to the menu button. I'm going to go to calculus, and then I'm going to go derivative. And I'm going to say I want f2 of x to be the derivative with respect to x of f1 of x. Press enter, done. If I type in f2 of x like this, I will get the derivative, which is 2x all over x squared plus 1. Now, the reason why that's kind of handy is because if I now go f1 of x and go control colon equals, and I go, let's just say nice and simple, x cubed plus 1. Okay, I've now redefined f1 of x as x cubed plus 1. And if I go to f of 2 of x now, remember this is the derivative of f1 of x, I get 3x squared. Okay, so f1 is the original function, f2 is the gradient function, the derivative, and if I redefine f1, then all the other functions get redefined as well. So that's kind of handy. I'll go back to the original f1 of x. Okay, of course we could do the same thing again by going f3 of x and go, I'll just show you a different way of doing it actually. So under menu is one way of doing it, or using the little button here next to the 9, and I can go to d by dx, which is right here. So you can just click on that, and that'll get you to the same point. I should have put a colon equals there, and I forgot. So I'll do that first. D by dx of f2 of x. So that will give me the second derivative. So now I've got f1 of x, which is the original function, f2 of x, which is the derivative, the gradient function, and f3 of x, which is the second derivative, or the gradient of the gradient function. So I can go f1 of x, there it is there, ln of x squared plus 1, f2 of x, and that is 2x over x squared plus 1, and f3 of x, and that is a bit more complicated, isn't it? Negative 2 outside of x squared minus 1 all over x squared plus 1 all squared. Now, the reason why it's handy to do this is that once you've got all these functions defined, it's really easy to find, say, let's say I wanted to know what the gradient was at x equals 3. I can just go f2 of 3, and there we go. The gradient is 3/5. Nice and easy. And what's the y coordinate? Then I can go f1 of 3, and that will give me the y coordinate, either exact or approximate. So all of these things are possible using these functions. If I then want to, say, for example, find the turning points of the graph, which I don't know if they exist for this one, I can use my solve function, and I can say, let's find the solution to f2 of x equals 0 with respect to x, and I get just the one turning point of x equals 0. Okay, is it a maximum or a minimum? I can go solve f3 of x. Remember, that's the second derivative. Sorry, my bad. I can go f3 of 0, and I can see the value is 2. So that means that the graph must be a minimum at x equals 0. And of course, we can go f1 of 0, and that will give me the y coordinate of 0 as well. So at 0, 0, we have a turning point, and at that turning point is in fact a minimum because the second derivative is bigger than 0. So there you go. There's a lot more that I could be showing you, but this is the bare bones of how you can calculate derivatives and second derivatives and use them in order to solve a variety of number calculations using your GDC. Hope that helps.